Next one we're talking about is the urinary system, how it all works. So, kidneys are crazy amazing. I mean, kidneys, every time I teach these lectures, I just get amazed again. Because kidneys are responsible for homeostasis, which is the maintaining of fluid volumes and body fluid composition within normal limits, okay? So, water balance. We'll talk about how much water, but the kidneys flush a lot of water out and they have to pull it back in, but it cleans us all, but it keeps their water balance. Electrolyte balance. Sodium, chloride, potassium. Potassium has a really narrow range in the bloodstream. What's good? Too much or too little, and it becomes problematic. And so it's really important to keep that range. And our kidneys help that all those stay in that range. Bicarb and hydrogen for the acid-base balance. The normal pH in the bloodstream is 7.35 to 7.45. Tiny, tiny, tiny little narrow range. And if you think about all the things that are on either side of it, the kidneys are responsible for that, for helping keep the body at that tight little range. Kidneys are also responsible for removing the waste byproducts of metabolism and muscle breakup and muscle breakdown, buildup and breakdown. Hormone production, the kidneys are actually responsible for producing antidiuretic hormone, renin, which is going to control blood pressure, and erythropoietin, which is going to regulate cell production. So the kidneys are actually responsible for those three hormones, which are all three vital. So we're talking about the kidneys. We got some major components. We start out with two kidneys. Kidneys, right back here. This is called the flank. When you read about something flank pain, think kidneys. Okay? This is why football players, they're on the back side. This is why football players have the pads that go up the back. Hockey players have the pads that go up the back. This is why we protect the kidneys now, thankfully. I mean, for years and years and years, we didn't know any better, and people would get really hurt. But that's where your kidneys are. They're going to filter the blood, and they're going to start the production of urine. And it's going to produce as it goes through. We'll talk about that in one of these next slides. There are two ureters that go from the kidneys to the bladder. One bladder, one urethra. The urethra on men is longer than the urethra on women. This is why men get fewer UTIs than women, because it's a much longer trail for all that bacteria to work up. The bacteria we were just talking about, it's a longer path for them to work up to get to the bladder. It's easy for them to flush it out. So here's what we're looking at. We got our two kidneys, the ureters, the bladder, and the urethra. So the anatomy of the kidney, I'm going to tell you right now, there's going to be a lot out there of a lot more specific parts. Do not get into the weeds about the other specific parts. You're going to learn a lot of other pieces. You're going to get into some more details. It's interesting to know, and it's helpful to understand, but do not worry about it. We are focusing on the cortex, the medulla, and the renal pelvis, those three parts in particular. The cortex is this outer area of the kidney. The renal pelvis is this middle part here. And then you got your medulla, which is this middle part here. These are very, very salty little medulla areas. The functional unit of the kidney is going to be this nephron here. There are 1 million nephrons per kidney. There should be, in a normal healthy person, 1 million functional nephrons per kidney. Okay? The kidney is responsible for filtration, reabsorption, and secretion. That is what actually makes the urine formation, this tiny piece that goes in and out of this kidney. Yeah?
Are we still going to call it the loop of Henle, or like the ascending and descending?
We call it the loop of Henle, but we call it the descending loop and the ascending loop.
Okay.
So
in my anatomy class, she got away from calling it the loop of Henle, so I wasn't sure.
And rightfully so, because the descending loop and the ascending loop have different function.
Right.
But we still kind of call it the loop. We just have to understand there are two functions depending on whether you're on one route or the other. So the renal corpuscle is going to be this piece here, this piece right inside here. It includes the glomerulus. It includes your Bowman's capsule, which is this piece here. The afferent arteriole and the efferent arteriole. Afferent goes away from the heart into the kidney. Efferent exits the kidney. Okay? Then we have the renal tubules, which is the next part, the proximal convoluted tubule, loop of Henle, and the distal convoluted tubule. That's going to be our urine formation. So this piece is the renal corpuscle, where we filter the blood into it. This is under super high pressure. One of our next slides is going to cover this. Let's go through this way. So here is the whole nephron. Our glomerulus, we got our afferent and our efferent, and you can see this capillary bed here. This is the peritubular capillary. Sorry, I couldn't come up with the word. I was thinking something different. peritubular capillary. So you see how much that weaves in and out? And because of that, right here, this glomerulus is under high pressure. Really, really heavy pressure. So it pushes the fluid portion of the urine, of the plasma, through what's considered a sieve. Think of a colander, right? Your spaghetti colander. You have brand new spaghetti colander is the same as a glomerulus, right? You're going to drain your spaghetti, the brand new ones, all the fluid portions are going to go out. Anything bigger is going to stay on the back side. It's going to stay in the blood. Approximately 20% of all the fluid that goes into this goes through the nephron, about 20%. So if you could do a hematocrit right there, it's going to be pretty high because 20% of the volume has left. 20% of the liquid portion is left. Goes through the proximal convoluted tubule, and you see there's a lot of capillaries around that area, and we'll talk about why in a minute. The descending loop and ascending loop of Henle, the distal convoluted tubule, and the collecting duct. So here's a bunch of the words. Each kidney processes more than 1 liter of blood each minute. The body has about 8 liters of blood at any time. So you can kind of see how much goes through there. 1 liter a minute, about 1,200 mils of blood. Greater than 120 mils of water is filtered out each minute. 120 milliliters of water is filtered out of the bloodstream each minute. Thank goodness most of it is reclaimed. Otherwise, we'd have to be drinking 120 mils of water every minute of all day long. At 1,200 mils per minute, it takes 7 to 8 minutes to filter the entire body's blood volume. So every 7 to 8 minutes in a normal, healthy body, the kidneys are filtering your entire blood volume. Crazy. Just crazy. So formation of urine, there's 3 different steps. We've got glomerular filtration. So water and molecules that are in solution are much smaller than the holes in the glomerulus, than that sieve, than that colander, so they get pushed out. That's our glomerular filtration. So fluid goes from the bloodstream into the glomerular filtrate. The next step is tubular reabsorption. The body's like, ah, just kidding, I want that back. Okay, a lot of water comes back at this point. The body reclaims. Reabsorption, the body reclaims what it needs. That's where it goes from the filtrate back to the bloodstream. Then tubular secretion is what the body gets rid of into the tubules extra. So it's the extra things we get rid of. It goes from the bloodstream to the glomerular filtrate. So certain drugs and excess hydrogen ions to balance the pH. So glomerular filtrate, like I said, this is super high pressure. Blood enters this under high pressure, and you get this glomerular filtrate that gets forced through the walls of the glomerulus. Cells and proteins that are too large to be filtered leave through the etheric vessel. So anything that's too big to get through the glomerulus. It enters the Bowman's capsule, and about 19, like I said, about 20% of the plasma gets entered at any given time. Approximately 180 liters per day. Normally, your glomerular filtrate is going to lack the cells and the proteins. So normally, glomerular filtrate means blood minus the cells and the proteins. Anything too big to go through. Molecules with a molecular weight of less than 60,000 are going to get through easily. Albumin has about a 67,000 to 68,000 molecular weight. So when we're looking at protein, albumin is the protein we specifically look for. We'll talk about protein a lot more later. But that is because it's one of the first step up to show our holes are getting a little big, right? We all have that favorite colander that we love, but over time, little holes break and your spaghetti starts weaving through, right? So that's what's going to happen over time. Your glomerulus is going to get damaged, especially if you're not good to your kidneys, right? And so what happens then is those holes get bigger and bigger, and all of a sudden we're seeing albumin as a protein in the urine. That's our first sign that, okay, wait, our glomerulus holes are getting a little big, things are sneaking through, we're starting to have some kidney disease. Filtered water with molecules include water, hydrogen, and bicarbonate, your salts, glucose, amino acids, and metabolic waste. So all of those things get filtered through. All of those things land in the glomerular filtrate. So tubular reabsorption happens most of the time here in this proximal convoluted tubule. Proximal, proximity, close. Distal, farther. You're going to have to keep those straight. Proximal, closer, distal, further. So in the proximal convoluted tubule, about 65% of the water gets reabsorbed at that point. So a lot, which is good, because remember when it's coming out of there, it's kind of sludgy, right? So we're getting a lot of that water back in, but we've cleaned it. We get about 15% of the water back in the loop of Henle and about 19% in this distal convoluted tubule, which leaves about 1% left. So everything filtered through, only 1% left is what gets left as urine. So most of the water and most of the product going through is going to come back to the body. So there's two types of reabsorption, active and passive. Active reabsorption, we use carrier molecules to transport it back and forth. You guys have had chemistry and A&P, so you understand that. Passive reabsorption, the molecules move from a higher concentration to a lower. We've seen that since, second grade. I think we first did our first science lessons in osmosis and passive reabsorption, or passiveness. Reabsorption in the proximal convoluted tubule begins as the filtrate enters it. We have active transport of our glucose, amino acids, potassium, sodium, bicarb, and chloride. We need that glucose back, right? The glucose all goes out, but our body needs glucose. So our body's like, just kidding, I need that back. And so I imagine, like, you know, somebody sitting there picking things back out, okay? Sodium, potassium, chloride for osmotic balance, those kind of go back and forth. Passive reabsorption, we get that water. We have to keep hydrated, so it puts it back into the body. And bicarb for pH balance. In the loop of Henle, the tissues around this are super high salt concentration. So we have some water that leaves the loop descending, but in the ascending loop, it's impermeable to water. So in the ascending loop, we're only losing some of the salts out. The blood supply to the loop of Henle is going to be the vasa recta. So that's all those capillaries surrounding that loop is called the vasa recta or vasa recta. So then we get to water reabsorption in the distal convoluted tubule. Water can be actively reabsorbed due to control of the antidiuretic hormone. So the body senses the need for water. Antidiuretic hormone is going to increase the permeability. So antidiuretic is going to reabsorb that water versus drinking a diuretic, which is going to let more water go out, right? So it's going to keep that balance. Water gets reabsorbed into the blood. Alcohol and caffeine are going to inhibit the antidiuretic hormone and cause the body to have more of a diuretic response. We're going to lose more water. I think we've all seen a night where we had too much caffeine or too much alcohol and be real dehydrated. That's actually what causes our headaches. So that's why they say, you know, if you're going to drink, make sure you drink water with it to stay hydrated because you're going to lose a lot of water. Sodium and potassium get reabsorbed in the convoluted tubule. At this point, we almost have urine when we get to the distal convoluted tubule. This picture is what I'm going to go over. So, in the kidney releases renin. The renin is going to lead to angiotensin forming in the blood. Blood vessels constrict, result in a rising blood pressure. Rising blood pressure results in the kidney slowing down its release to renin. So it's a loop. Now, it also stimulates the adrenal cortex, which is going to release aldosterone, which is going to tell the kidney to reabsorb more sodium ions, less water loss in the urine, blood volume increases, which is also going to cause rising blood pressure. So it's actually twofold. The renin, angiotensin to blood vessels constricted, also to the aldosterone, which is going to cause less water loss. I'm not going to test you on this, but take some time to really think about what's happening in the kidney because of the blood pressure and the loops. Secretion in the distal convoluted tubule. Now, it does occur throughout the tubules, but in the distal, we specifically removal of drugs, penicillin, oleic acids, waste products of cellular metabolism, and secretion of hydrogen ions regulating the blood. So the distal convoluted tubule is where the hydrogen ions are going to maintain their balance. If nothing else, think of the distal convoluted tubule for hydrogen balance. That's going to be what balances the pH. Remember that tiny little range we talked about bloodstream pH? Most of that occurs in the distal convoluted tubule. When we get to pH in a couple lectures, we'll talk about that and how it works a little bit more, but it happens in the distal convoluted tubule primarily. Does it happen elsewhere? Yes. But that is really where that final balance really takes place. So we move into the collecting ducts. The collecting ducts are larger. The million nephrons are all leading into one collecting duct, so the urine, it's collecting all the urine that the nephron is made, and it goes from there to the ureter, to the bladder, out into the urine cup. You see that little cup there? Yeah. Always one of my favorites, tiny little urine cup. But anyway, that is urine then at that point. So the final composition of of urine, 96% of urine is water. Largest component is going to be water. Now, there's any reading, something says 94% in one of the charts. I'm not going to, the largest component is water, right? Then it's 2% organic compounds, 2% inorganic compounds, and 1% are miscellaneous. But Leah, what does that add up to? 101. But Leah, that's 101%. What causes that? Think back to your lab math. Bad rounding, right? This is why we tell you when you're doing your math, go to a certain unit until you get to the end, because if you just round off each one individual, you're going to get 101%. Okay? It's fine for our purposes, but this is what I always keep this in here because this is what bad rounding does. Reiterates what you learned in math. So, the largest component after water is going to be your urea. 55% of this 2% is going to be urea. So that's the take home. Everything else is pretty low. So the largest component is water. The second largest after water is urea. You might see that again. Physical characteristics of urine. And we talked a little bit about this in the last lecture. We're going to talk a little bit more here, not too much. 1 to 2 liters per day volume. Average 1,500 mils. Another day, another 1,500 mils. pH varies between 4.6 and 8. Why do we care? Right? I mean, that's the range. We'll talk about more with pH when we get to pH. You do have a high protein diet, you're more likely to have more acidic urine. A high vegetable diet, you're more likely to have more average of a more alkaline urine. But still, it's going to go either way depending on time of day. We'll talk about all that when we get to pH. Specific gravity, 1.003 to 1.035. Again, why do we care? When we get to it, we'll talk more about why we care. The color, due to urochrome. You're going to see that over and over and over. The color of urine is due to urochrome. There are 2 other elements that sometimes have a factor in it, but urochrome is the primary coloring agent in the urine. Abnormal constituents of urine. We do not usually see albumin. When we see albumin, our holes in our glomerulus, our sieve have gotten a little bit big and the albumin's getting through. Glucose, we usually don't see glucose. The other thing you need to know, by the way, know the words. Albuminuria, albumin in the urine. Glucosuria, glucose in the urine. Hematuria, we don't usually see red cells. When we do, it's hematuria, which is red cells in the urine, or hemoglobinuria, hemoglobin in the urine. Go back to your basic lab skills, word root, word suffix, prefix, right? We're going back to the basics. If you can't remember what it is, break it down and figure it out. Leukocytes, we see pyuria. PY means fire in Latin. So when we have an infection, it's PY. Ketones, ketosis, ketones in the bloodstream. Ketouria, ketonuria, ketones in the urine, ketoacidosis. Bilirubin, bilirubinuria. Microbes, bacteria. So those are all things, learn all those words. Key terms, here's all your different key terms that you need to make sure you know what they mean. There's more key terms, you need to make sure you know what they mean. Here's your objectives. Again, all the objectives are in Blackboard. I'll show you where that is here in just a minute to make sure you all can go to that. Study from your objectives. Every test question we give you comes off of objectives. Every quiz question, every test question comes off of an objective. So it's really important to know that.